So logistics for the exam, just like last time, you can have a cheat sheet where you can put whatever you want on the front of an 8.5 by 11 sheet of paper. I would recommend a few things that you put on there, and maybe I'll get to that in a little bit to talk more details about it, but it can be whatever you want. And the exam will be similarly structured to the first one. There will be some multiple choice conceptual type questions and some calculation. It usually skews towards the calculation type questions in kind of a 60-40 or 66-33 kind of ratio. Um, as for the length of the exam, it's not finalized yet, so I am not sure, but the goal is that it does not take as long as exam one did. I am pretty much just looking at last year's exam and coming up with similar questions to that one. So I will attempt to make it the same length as that one was, and that one did not go over time, as far as I can remember. So I want to start with specific questions, and then just based on whatever questions there are, I'll get into maybe more details on certain sections in the chapter, rather than just trying to jump at the whole chapter at once. So are there specific questions to start off with? Okay, well, if not, give me 1 second to get my laptop plugged up, and oh, I see. Okay. 26. I will get that just a second. I'm going to plug my laptop up and then we will look at 26. Okay, so I can pull up the blank copy and go through the entire example, or I can just talk through the solution from the written out ones. Which would you prefer, Bella? Okay, so for 26, we have an uncharged capacitor. So I would highlight uncharged because we saw that it's a slightly different set of equations depending on whether we're talking about a capacitor that's charging up versus discharging. So this would be the case where the capacitor is going to charge up. It's uncharged right now. I'm given the capacitance, and I'm given the value of the battery. That would be in the context of RC circuits V0. I'm told about a resistor, but I am not told its value. We have a RC circuit formed by those things. I'll just draw in a little circuit. I'll put my battery over here. Battery, switch, resistor, and capacitor. And battery is 12 volts. Resistor, I don't know, so maybe I'll just call it R. And then the capacitance is 5 microfarads. We close the switch, and we are given the time constant. So symbol for that is tau. We want to find the maximum charge on the capacitor. So in general, the idea of an RC circuit is that when we close this switch, charge is going to flow from the battery onto one plate of the capacitor. That's going to push charge off of the other plate, and we will build up charge on either plate as a result. That's going to happen until the voltage across the capacitor is exactly the same as what the battery can provide. And you can think of that very similar to if we have two batteries going in opposite directions from each other. In the notes, we had something like that with Kirchhoff's rules. The batteries are kind of fighting to determine which way the current will actually flow. For the capacitor, the only difference here is that it's the battery that it's representing is changing its voltage, which batteries don't tend to do, but this is one that is charging up. You're getting more and more of a voltage across it. So it's acting like a larger and larger battery as time goes on, up until it's just as large of a battery as the real battery over here, and they're in complete opposition to each other and no current flows anymore. So the maximum charge on the capacitor, we're going to reach that point when we have the maximum possible voltage across the capacitor, which is going to be the battery voltage, 12 volts. To find the value of the charge, then, it is directly related to the voltage across the capacitor. This is true for any capacitor, not just for this RC circuit stuff. You multiply the voltage by the capacitance to get the charge. So Q is charge, C is capacitance. That's one that's pretty commonly mixed up, and people will say that C is the charge, but it is capacitance. Q is what we always use for charge, and this is that 12 volts. So to find the charge, we just say, all right, this is how much voltage we have across the capacitor. This is the capacity of the capacitor to store charge at that voltage. You put those together, you get how much charge is actually stored. And then just writing it in terms of SI, the prefix micro is 10 to the negative 6. Any specific questions past that, Bella? Okay, all right, great. So we didn't actually need the time constant bit for 26, but it did become useful for 27. If we wanted to find the resistance, we could do that. We weren't asked about it, but say we were. This other equation comes in handy, which is that the time constant is the resistance times the capacitance. This is just stating that the time it takes for the capacitor to charge up depends on both how much charge the capacitor can store and the resistance to the flow of charge. If you increase either of those, in other words, you kind of get a bigger bucket for charge to flow into, or you use smaller pipes, letting less charge flow at a time, it's going to take longer for the capacitor to charge up in that circuit. Okay, maybe before there's other specific questions, that's a good time to mention some things about the cheat sheet. So I'm just going to add a page. And just state a couple things that are maybe worth saying something about on your cheat sheet. So first, there's nothing wrong with examples to go on a cheat sheet because they can kind of remind you how to do a problem, but they should not be, in my opinion, the main thing that is on the cheat sheet. And my reasoning for that, I think examples are a trap. And the reason I think that is, and correct me if I'm wrong here, if you have examples on your cheat sheet, then when you get to a certain problem and you don't know how to do it, what you end up doing is looking at your cheat sheet and seeing if you can find a problem that is almost exactly the same And then even if it's not exactly the same, you try and sort of map the example problem onto the exam problem until you can massage some number out of it. That's a trap because then you're kind of forcing yourself into a certain solution that may not even be right. It's just what the example is doing. And maybe the example is not similar enough for that solution to even apply. So what might be better is if you at least change perspective on what an example is supposed to do for you. It's not supposed to tell you how to solve a specific problem. It's telling you how to solve a certain class of problems. And what I mean by that is, say, for like a series and parallel kind of circuit, you may have on your cheat sheet something like this circuit, but then on the exam, you get something like, I don't know, maybe something like that. Those are different circuits. So if you do the exact same thing you did for this circuit to figure out, say, a current or a voltage for one of these resistors in this circuit, you're going to get the answer wrong. But if in your example you write down what the general idea of solving the problem is, that is more applicable to both problems. So for series and parallel, the general idea is first you find the equivalent resistance. And you do that by finding series and parallel resistors two at a time. You can sometimes do more than two in one pass, but I think it leads to more mistakes typically. So what I've been telling people, and I don't know, I kind of wish I'd said it this way sooner. You may be drawn to say these are in series. That's a very common mistake because sometimes it's hard to be sure. But I feel like you can be pretty darn sure those are in parallel. So don't attempt the two in series because you're not sure about those. Just do the two in parallel first because that's the one you know, and then redraw the circuit. So the next step, it's really a sub-step of part one, is redraw the circuit each time. You combine two resistors. So I would get to this point, see that these are in parallel. I'd find the parallel resistance of those two, and then draw a brand new circuit if it'll cooperate with it. This resistor hasn't changed, I've not done anything with it, but now the two over on the right have become one single equivalent resistor. And this is my new circuit. And now I can see very clearly that those are in series. So pick the resistor pair that screams at you that it is in series or parallel. Others may whisper it at you, may say, I kind of look like series or parallel. But typically there are two that will just scream. Start with those and then redraw the circuit. I think there's kind of a rush to get these kind of problems done and find the equivalent resistance in one shot. That's where almost all the mistakes come from. Just take the time to do it a little bit by a little bit. And if you do, that'll actually end up being faster than trying to figure out where the mistake was, trying to do it all at once. Okay, so once you're down to one resistor, oops, sorry. When you're down to one resistor, which would be the equivalent resistance for the entire circuit, find the current leaving the battery. From V equals IR. Because if you have only one resistor in the circuit, then that equation is pretty straightforward. This is just the battery voltage. This is the current leaving the battery, and this is the equivalent resistor. After you do that, work your way back up. And by that, I mean, okay, if you followed this process, you would have found this circuit and then simplified it to, with these two being in parallel, you would have simplified it to this circuit. And then with those two being in series, you would simplify one last time to this single resistor circuit. If you know the voltage and the resistance in this very simple circuit, the current is just V over R. But you can take that information and put it in both of your other more complicated versions of the circuit, this one and this one, because that's the current leaving the battery. It's got to be the same in all three cases. From there, specifically what you want to do, part A is series have same current. Parallel have same voltage. So if I'm starting from the simplest circuit and working back to the slightly less simple circuit before it, I know that since these two resistors were in series, they're going to have the same current as each other, and that's going to be the same as the current through their equivalent resistor. In other words, this current right here is what's happening through both resistors. But that I can then use to say, okay, now I know specifically the current through this resistor and specifically the current through this resistor. So that means I can find the voltage specifically across this resistor from the current through it times its resistance, and same for this one. Once I've done that, I know everything there is to know about that version of the circuit. It's not the full circuit. It's not the most complicated version that we started with, but I know everything there is to know about it, at least. So you'll combine that idea of series and parallel relationships with V equals IR until you know everything about the circuit. And then, and only then, move one step up. So back to the even less simple circuit. So in this case, that would be back to the original circuit. I work back to it by realizing, okay, now I know the voltage and current for this equivalent resistor. It's really two resistors in parallel. But since they're in parallel, they're going to have the same voltage, and they will have that same voltage as the equivalent resistor. It would be the one I found right here. So whatever that is would go right there. And then I could find the current through each by saying I is V over. This one I'm already done with because it's not an equivalent resistor. It's the one that I actually had in the simpler circuit. So if that bit is not clear, an actual explicit example is, oh, in the practice exam already. This part, this full analysis of the previous circuit. It's talking about this circuit right here. And you can see I did the exact steps I was talking about. First thing I did is in steps of two resistors at a time, I picked the ones that looked most obviously series or parallel, found those, combined them into one equivalent resistor, did that again because I realized that equivalent resistor was in series with another resistor, redrew the circuit again, found the equivalent resistance until I was down to just one resistor. Then I used that to find this current leaving the battery, and then I worked my way back up from there. So once I found the current leaving the battery, I could go back to this slightly more complicated circuit. I could realize, okay, this resistor was actually two resistors in parallel, so they should have the same voltage across them as this individual resistor. That's where the 6 volts came from for that one, and then it's not drawn here for that one. And then I could find the current through each resistor by saying it's V over R. Then I work back, because now I know everything about that version of the circuit, to the less simple one, and just keep doing that until I know everything about that version of the circuit, and then I move on until I know everything about the original circuit. In the process, I really never worried what the questions were, but now I can look back up at them and I could answer all three of these questions just by looking at my work on this page. So the top version was doing it a series in parallel. The bottom was with Kirchhoff's rules, which, if that is more comfortable, it usually isn't for most people to do Kirchhoff's rules, but if it is, that's also a way you could do it. Okay. My head is all over the place. I think it's the pollen. So examples are a trap, but representative examples are good. So you don't really want to have like step one, like for this specific resistor. Like I wouldn't copy down the example I just talked about a second ago, but I would say this is your general process for finding them. And you could then include the example I just talked about as one kind of representative example, just reminding yourself that really this stuff, the bracketed stuff, is what works for any problem. Depending on which problem you're doing, the steps are a little bit different each time. If you can do that for different types of problems, then you're in a good spot. And so for other types of problems, it might be that I know that if I'm given a resistivity and I need to find the length of wire, it's this equation that helps me do that. If I'm given current and I need to know how much charge moves through a certain circuit, it's that equation. And so being able to recognize what equation is used with what is important. And the first step to that is, and this is another kind of put it on your cheat sheet, or at least my recommendation, write out a list of variables. We think we know what the symbol for every kind of quantity is until we get to the exam and we don't. So you have a table that's like, okay, variable, oh, the quantity first, variable, and then unit. I just went through chapter 20 and just did this for every kind of commonly seen variable. I would see charge, I always use Q, and the unit is always coulombs. C. Current, we use I. The units are amperes or amps, abbreviated A, and so on and so forth. That way, if you get to a problem and you have no idea what to do, at the very least, you can see that you're given either charge, and so you know that's Q, or you're given the unit, it's coulombs, and you also know that's Q, and that narrows down the equations that could possibly be useful from this list, because not all of them have Q in them. So let me see if I can find a specific example like that. You can see that's why I'm underlining these things as I go through the different problems. Let me go back up. So ones like this one, it's kind of straightforward just because of the information that's given, but it's the same idea. If I didn't remember that the symbol for resistivity is rho, I may never decide that I should use this equation. But it is one of only two in this entire list that has rho in it. The other one is this one. I was given nothing about temperature. I was given nothing about this alpha thing. So it's probably not that one. It's the other one. So turn it into a game as much as it is needed to solve the problems. And so on a first read through of any problem, on a first read through of any problem, that's what I'm doing. Is I've gotten to the point I kind of do it mentally now, but I'm underlining the words that are important quantities, writing the variable, and then for ones that maybe are not so commonly, like they don't have a definitive symbol we use every time, I might come up with my own. And most of the time I can kind of fill in the blanks in between. So length of the wire, and that's L, and then what is it asking for R? That narrows down my possibilities. I might get a little concerned because I was not given area. But to me, that just screams, oh, I just need another equation in addition to this one. And that would be finding the cross-sectional area of the wire. How well do we have to know about time constants? I would say conceptually, it's good to know that it's the time it takes for a capacitor in an RC circuit to charge up or discharge by 63%. But really, even more important is how can you increase or decrease the time constant? And the only ways you can do it are change the resistance, change the capacitance. Past that, it would just be like, what is the time constant? So I can't say I'm really expecting you to do a lot with this kind of equation and saying, what is the charge after 5 seconds or whatever? It's more things like what is tau, and then what is the maximum charge? So more like question 26 than 27. Okay. That was, I think, my whole rant about cheat sheets. But just don't let it be the thing like a crutch, because the second you don't find the thing you're looking for on it, if that's how you're using the cheat sheet, you're going to get stuck. And I think it creates a mental block to get stuck in that way too. And it's hard to dig yourself out of that. All right. Other questions?
I have a question on example 18.
Okay. Yeah. What's the question?
So I'm confused why 30 and 60 have the same voltage across them, and why it's less, like 6 voltage is less.
Okay. So let's look at our original circuit. What do you notice about the 30 and 60 ohm resistors?
And they're parallel.
What's true about parallel resistors?
Um, they have the same voltage.
Mm-hmm. Okay, so that's the first volt. Now I notice that those together are in series with this resistor. What's true about the voltage for series resistors?
So 30 and 60 together
Mm-hmm.
have the same voltage as the series. Oh no, the 10 has the same.
No, so the 30 and 60, they have the same voltage as each other. And that
Okay.
voltage is the same as their equivalent resistor, the voltage across it, whatever that number was. I don't know what that number is, like just looking at this circuit. I just know it's the same number. Okay, so um, past that, I know that resistors in series add. Okay, so the 30 and 60 are in parallel. They have the same voltage as each other. So in my head, I kind of mentally replace them with a single equivalent resistor. So these are gone. That is the parallel addition rule. So it's a 20 ohm resistor. But I see that now I've got that resistor in series with the 10 ohm resistor. So can the 20 and 10 ohm resistors have the same voltage across them?
No.
No, they're in series. They'll have the same current through them, but they don't necessarily have the same voltage. And more importantly, even than that, is that they don't have the entire 6 volts across either one individually. You do have, you're dropping 6 volts as you go across both together, because that's how you get back to kind of the negative terminal of the battery. And same for this resistor. I can tell that this has 6 volts across it because it's sharing terminals with the battery. That's that thing of it doesn't matter how you get from one point to the other for voltage, it's path independent. And so since this point is, aside from wire connecting them, the same as this point right here, and this point is the same as this point right here, there's no resistors in between. It's like I've just got that going on. And so that 20 ohm resistor has to have the same voltage across it as the battery. And then these all together have to have the same voltage across it.
Okay, that makes a little more sense.
All right. Other questions? And by the way, Kennedy, the stuff I wrote here is one way to approach it. You could also do this part that's on the next page and not treat it as a conceptual question. It can be a calculation question where you explicitly figure out which resistor has the largest voltage across it. You would end up finding after doing this whole process that it's this one right here. So it has all 6 volts across it.
Thank you.
Mm-hmm. What else?
Number 14.
So this one is a little bit odd compared to the others. I wouldn't necessarily say there's one exactly like this. The main thing is the power. And so I'll come back to that. I would say one's more like these questions up here are typical. But this one kind of asks you to think past the series and parallel stuff and figure out something about this circuit. So what was your question about it? Kennedy?
Oh, I'm sorry. I don't know. It's like it's like it's going in and out or something. I didn't know what you said, but for me, it was dividing the current, like to get the bulbs. I'm confused, like why dividing the current gets the bulbs,
So
and why is adding the currents like
that part right
why?
there?
Yes.
Okay. So the first thing I did was figure out how much current is going through each individual bulb. And I could do that because I knew how much power was used by each bulb. That's the power rating. And then I knew the voltage across each one. The reason I knew the voltage across each one was because they're all in parallel with the battery, meaning they're going to have the same voltage as it, 120 volts.
Mm-hmm.
So from that, I can find how much current is going through each individual bulb. I would see, okay, there's 60 watts for this bulb divided by 120 volts. That's where this half amp comes from. There's also 60 watts across the second bulb and 120 volts to that half amp, and so on and so forth for however many bulbs there are. So say I had just 2 bulbs. How many amps of current would flow through the circuit?
Just 2 bulbs.
Mm-hmm.
Okay, so get rid of one. So it'll be 1.
Yep. Okay. Say I had 3 bulbs. How many amps of current?
Um, okay. Well, then it will go back to 0.5.
So it's I would think of parallel as like nothing really changes if we just cut this whole thing out. That's why outlets are wired in parallel. It's that disconnecting one appliance is not affecting what's happening to the others. So we would still have a half amp of current, whether we had two bulbs or we had three. The battery would just have to supply more current if we had three bulbs. So with three, it would be 1.5 amps. It would be a half amp for each bulb.
Oh, okay. The total current.
Yes, yeah. So the current that's
Okay.
leaving the
Okay, that
battery.
I was thinking each. Okay, that makes good.
Okay, okay, yeah. It's always going to be a half an amp for each bulb. So if we had one more bulb on top of that, then
Okay.
it would have half an amp going through it, but that would mean the total current leaving the battery is 2 amps.
But since they're in parallel, wouldn't it be different currents? But
It
they're the
would,
same.
it, you're right. In general, it would be. The reason I know that it's the same here is because these light bulbs are identical. So it's like I have a bunch of identical resistors.
Okay.
So what has to be true for them is that the voltage is the same for each, even if I had completely different light bulbs, completely different resistors for each one, because they're in parallel. It doesn't have to be true that the current's the same for each in general for parallel resistors. In this case, it's true because they are identical resistors. Does that make sense?
Yes, that makes more sense. Yes.
Okay. Okay, so we were on that train of saying, okay, if I had four bulbs, I've got 2 amps leaving. My limit is 9 amps. So how many light bulbs is it going to take for 9 amps of current to leave the battery?
You said the limit is 9 amps.
Yeah, so this fuse,
Okay.
it trips
So
when 9 amps flow.
I'm confused how to figure that out.
Well, we figured out how many bulbs it takes to get 2 amps, right? It's going to be four bulbs. To get 2.5 amps, it'll be five bulbs because you'll have another half amp going through that one, meaning 2.5 have to
So
leave the battery.
adding each half amp until you get to 9.
Yeah. Alternatively, you could see how many times one half an amp goes into 9 amps. It's really the same question.
Okay.
It's how many bulbs, how many half amp things are needed to go into the 9 amps that are going to be going through the fuse. That's where this division comes from.
Okay.
But if you wanted to count it one by one, you totally could. You could say, okay, with one bulb, it's a half amp. With two bulbs, it's 1 amp. With three bulbs, it's 1.5. Four, it's 2. Five, it's 2.5. And keep going until you get all the way to 9 amps. And you would realize you are on 18 bulbs at that point. So
Okay.
does that make
That
sense? If it doesn't,
makes more sense.
okay. So maybe
Yeah, I understand.
okay. Yeah, so dividing is just the shortcut. You could feel free to think of it as I gotta keep adding bulbs until I actually blow that fuse by
Okay.
saying, all right, I'm at 0.51, 1.5 to 2.5 amps with how many bulbs I have now. I can still add some more bulbs before I reach that 9 amp limit. If I add another bulb, I'm at 3 amps. If I add another one on top of that, I'm at 3.5, all the way until I've added however many bulbs it takes to get to 9 amps. And that how many bulbs it takes would be 18. So to not blow the fuse, I need one less bulb than that. 9 amps blows the fuse, anything less doesn't. So that's why I said one
Okay.
less.
Yeah, I get it. I get a little bit more.
Okay, other questions? 19. Cool. Okay, so 19, I recognize this as a cure cause rule problem because I see more than one battery. Usually that's a pretty good indicator that series and parallel is not going to help you very much because we don't know what to do with batteries in series or parallel. Even if we had rules for them, sometimes in these pictures, they're not in series or parallel anyway. This is one case where that's true. They're not in series or parallel in this picture. So my brain immediately starts applying Kirchhoff's rules. And that would be another good cheat sheet sort of thing is not one single example, but just a representative example, which has 1, 2, 3, 4. Here are the things you do to apply Kirchhoff's rules. And there is, kind of a nice, convenient little boxed thing in the notes that says, here are steps 1, 2, 3, 4. So it might be helpful to copy that down and then just put an example beside it to give you the idea of what you do, but don't rely directly on the example. Don't use it as like, if I don't have exactly this circuit, it's over. Okay, so for this specific problem, I'm gonna clear all this stuff off for a second so that we can see the I don't know, the naked circuit and like how I would approach this as I'm first seeing it. So I think the hardest step in Kirchhoff's rules is step 1, which is to label any junctions and then label currents based on those junctions. So a junction is anywhere that you see 3 or more paths for current to flow. I see 2 spots like that. This one right here and this one right here. You can have junctions with more than 3 paths. It's a little less common for the circuits we're seeing, but as long as it's 3 or more, that is a junction. It's not for 2 because that's just a corner. This right here is a place where 2 or more options are present, but that's just current flowing around the corner. So if we see 3 or more, that's a junction. I see 2 of them. And then really the hard step is this leap of faith you have to take, which is just deciding which way current flows. It is for once your choice how you want to do it. So in this picture, I may have absolutely no idea whether current is leaving or entering the junction from this side. Same here. I may have no idea. Same here. So I just pick. I just guess. I don't know. Maybe it's this one, maybe that one, and maybe that one. So these are my guesses for which way current flows into and out of that junction. It probably wouldn't flow this way because all 3 are flowing into the junction, and that will be a little bit weird physically, but it's entirely okay mathematically. And Kirchhoff's rules are really more a math tool to get the right answers. So this is okay to draw it this way. But for however many currents I've had to label, I give each one its own name. So I could call one I if I think it's more special than the other 2, so it doesn't need a subscript, or I could just call them I1, I2, I3. And if I have been cutting out, please let me know because I keep getting that my internet's unstable. I'm not sure why. There's other people in the house on the Zoom call, so it must be that. But once I've done that, you'll notice that actually is different from what I labeled originally, and that's okay. I can still solve the problem this way. I'm just going to find out that 1 or more of the currents I labeled now is going to turn out negative. That is the only issue that will arise. It'll come up at the very end of the problem, and I don't have to redo anything. I just have to recognize that the currents, the way I drew them, some should be flipped over. So the next bit is just, I don't want to over-label my currents in the sense of maybe I only need 3. How I can tell is I see that these 3 things are in series, the 16 ohm, the 18 volt, and the 25 ohm resistor. And so the current through the battery has to be the same as the current through the 16 ohm resistor and also the same as the current through the 25 ohm. In other words, this is also I1. For this middle branch, if it's I2 going into the junction here, it must be because it came from over here. And then last for I3, if it's going into the junction from here, I track it back to the other side. It must have been leaving this junction. Okay, that's all my currents labeled, and I didn't over label. I don't have an I4 where I could have just used one of the three I already had. Then I set up the junction rule. It's going to be different than what I've got written because I labeled my currents differently. I would say I've labeled all three as going in, I1, I2, I3, and none going out. So this would be my equation instead. So I just want to pause there. Do you want me to go through the loop rule bit with this too, Bella? You hear me, Bella? Can anyone hear me?
You just keep cutting out, so I don't think anyone heard the question. I just heard you say you were stopping for a minute.
Okay. So I was just asking, should I continue with the loop rule, or was this where the confusion was?
My confusion came from the junction. So thank you. I understand the loop.
Okay. All right. And so the loop rule would be a little bit different based on how I've labeled my currents, but otherwise it's the same process.
So I have a question about this.
Yeah.
How do you know how to label the current?
In what sense?
Like how to label like I1, I2, and then where where can you see there's a junction A and junction B?
So as far as why I called this one I1 versus I2, or why it's the direction it's labeled? So it is the confusion with the fact that I decided to draw the arrow this way and then down over here this way and then this way, or is it about that I called this one I1, I called this one I2, and I called this one I3? So
Like
the two.
how you drew the currents. Like, okay,
Oh,
well, I think I kind of see like it going out of the battery,
mhm.
but no, I don't understand why I1 is because I
So
would think I1 would be I2. I2 going this way, then I1 would be I2. I don't know. I'm kind of confused.
okay, so I think the question you have is the thing I'm saying about it actually doesn't matter. It really is your choice. So I don't actually know that I1 goes this way. It could go this way. Uh, it could have gone that way. That would just change my junction rule to now I1 is not going in, it's going out. I could have labeled that as I2 instead, and then called the one that I'm calling I2 right now, I1. In that case, now I've got I2 going out and I1 going in. So my junction rule would become this. The equations change, but they don't change so significantly that I'm going to get a completely wrong answer. I'm just going to get an answer where some of the currents are negative if I drew them in the wrong direction. So any choice is correct here. It
Okay.
literally any choice.
So the current going into the battery.
Mhm.
So like that's where you draw the arrows, right? Like I2 would be going in.
I'm
It-
looking at whether I2, oops, sorry about that. I'm looking at whether I2 is coming into or out of this junction where three currents kind of exist simultaneously. So I don't care about the batteries in this
Okay.
kind of
So
process.
you're looking at the where the resistors meet. Well, not where the resistors meet, but
Like where three wires meet. I don't even care what's connected to the wires. It's
where
just
you see a split of parallel.
yeah, where I see a split is probably the best way to phrase it. If there is a way current can go more than one way, you're looking at a junction.
Wires meet. Okay. Way current can go.
So,
Okay.
like, if I had a circuit that was just this simple, like that's a battery, there is no other way a current can go other than around this, or it would go the other direction. But that's it. That's my only options until I add another branch. And then current can make a choice. It can go either of those two ways. That is a junction.
For this question, can you use the junction rule or the loop rule to get the same answer, or do you have to do both of them?
You have to do both because we have three unknown currents. If you have three unknowns, you need three equations. The junction rule only covers one of them for us. The other two come from applying the loop rule to two different rules or two different loops in the circuit. Okay. Other questions? And I'm
So
happy
does
to.
the loop
Yeah.
depend on the junction?
It depends
Does
on
the
how you labeled your currents.
label, I
Yes.
mean label the currents, that's what I meant to say.
Yeah. So if you look over at the way I originally had it, this stuff over on the left-hand side, I've labeled positive and negative for the resistors aren't actually there anymore, but where the resistors were based on which way I drew the currents. So I had drawn this current going up through this branch, and that's why I called this positive and this negative. Over on my picture I'm looking at now, the way I've labeled my currents, that would again be true because the current's flowing the same way, and we draw positive and negative to say current flows high to low potential. But one that would be different is, say this, or wait, I've got that the same too. Where's one I did different? Oh, I had this flipped over before. Let's go back to saying I2 was going into the junction. I'll clear this out first. Okay, so I had this was I2, this was I1, and then this I called I3. Looking at that, I see that my current right here goes down through the resistor. So if I want it to be going high to low potential, this should be at the high potential, this should be at the low potential. If I go over to my resistor on the right-hand side, I have a current going up through it. So if that current is going from high to low potential, this should be the high, this should be the low. And so you can see that's exactly the opposite of how I had it labeled originally, because my current, I decided, is in the other direction in this attempt at the problem. But it's okay either way. The math will work out. Um, Other questions?
So just to be clear, the junction represents the wire splitting.
Mm-hmm. And
Okay.
if it helps, imagine these wires as pipes. Okay, water's flowing through the pipes. Well, as long as it's just flowing through one pipe, it's only got one way to go. But as soon as it gets down to here, it's got options. Water could flow that way, water could flow down. That's how you know you've got a junction. So like in actual pipes, you got some water flowing. It can go two separate ways at this branch. That's what makes it a junction. The circuit is just like that. This is a place, say the junction on the left is the one I'm really circling right now. That is a place where current, charge has a choice of which way to go. That's how I know it's a junction. All right. Let's see. Ashley, James, Leah. I don't think I've heard much from y'all. Do you have specific questions?
I didn't have any specific questions. I was just following along, but just to make sure on this question. So even if we have this question on an exam, if you put negative, it won't be counted wrong if it's the same answer, will it? Or would you prefer us to just change the direction and resolve it?
So I guess what I really want to stress here is the way I did it originally is what led me to currents of 0.52 amps, 0.146 amps, and 0.67 amps. So I got them all positive at the end of the day. Say I had drawn just one current differently than I did in my original solution. Let me clear this again. My original solution had I going this way, I1 going this way, I2 going this way. So I2 goes into the junction, I and I1 leaves the junction. Say I had done that just barely different by saying that I1 went into the junction instead of out of it. If I went through this whole process all over again, the only thing that would be different is that, where'd he go? That's I2, I1, this one. This number would have come out to negative 0.52 amps instead. And so that would tell me automatically that this should go the other way. I don't need to resolve. I know. And now I'm back to my original solution. So negatives, that is it. That's the only issue they have. And so you know that the current should have gone the other way. There is no resolve. Like you're still done once you get a negative current. You just now realize that the current went the other way in the first place.
Okay, and one more question. Could I use it like to determine the direction of the current, like flowing away from the positive and towards the negative, or would that be wrong in another way?
So let's maybe this will help. So let me put
I
that
can't
back.
hear you. It's kind of breaking up.
Oh, sorry. Better now? Same? Worse?
It's better now.
Okay. So let's look at I, the way I've got it drawn. Because of the way I drew it, I would call this the positive terminal of the resistor and this the negative terminal. Okay. Say I change my mind. I say, I don't like that. I want to do it the other way. I want current to flow the opposite direction. Well, current is still supposed to flow from positive to negative. So I got to reverse those. That's it. So current flows positive to negative. And all of this is, I know there's so many little things for Kirchhoff's rules, and it is difficult to like do all of them. But the rules that are in the notes are specifically all you have to do. And I think all the trouble that comes from Kirchhoff's rules is more just not wanting those rules to be so easy, but you do just apply them as is. You just pick current directions. They can be whatever you want. Then based on the directions you picked, you pick whether the terminal is positive or negative, current flows high to low, and then you do rises and drops. So it's not like some of the other physics stuff where it's like you really got to think through, like, is it accelerating, is it not? It really is just an algorithm that just gets you the right answer if you just go step 1, step 2, step 3, step 4.
Okay.
Yeah.
Just one more question about it. So you said not to do more than 3 currents, and then when we solve both, do we have to add the loop rule and the junction rule together, or are they like a separate thing?
So they are 3 equations that have 3 unknowns. So it would be that you really have 3 separate equations that need solving. On a Kirchhoff's rule problem, I would just ask you to get to this stage, and you wouldn't even have to solve for I1, I2, I3. I just want you to set up the loop and junction rules, because once you've done that, the rest of the problem is just algebra, and that's not what I'm testing. I'm just testing on, do the loop and junction rules make sense? So you wouldn't even actually need to find these. That's just telling you what that last step is.
Okay, thank you.
So my actual stopping point on an exam would be getting these 3 equations. Okay, so I saw James said his question was answered. Leah, was there a question from you? And then, no, what's happening with this week? And can everyone still hear me?
Yeah.
Okay, I thought it just completely crashed on me. It's acting a little weird. But if there are no more questions, maybe that's a good place to call it anyway.
Yeah. Thank you.
Yep.
I'm gonna leave. Bye.
All right. Kennedy, did you have any other questions?
I'm making sure. I think I'm good. Yes, sir. Thank you.
Uh-huh. Okay, I'll see you on Friday.